Like a lot of the poker hand problems, those fall into a general category. They're called ball and earn problems. These are problems where you're asked to consider a set of objects that are split into groups, usually referred to colors. So it's like a bucket with a bunch of balls, and some are red, some are green, some are blue, or various other colors. These colors could be anything. It could be a set of people that you're considering, and you could be grouping them by gender. The gender could be the 2 colors or 3 colors, however you want to do that. You could have kind of ranges of ages, could be different colors. So people from up to 18 could be one group, 19 to 30 could be another group, and so on. That would be considered like another color. And you're just wondering how many samples of a certain type with a certain distribution of different colors are possible. So again, sampling from a deck of cards is really just a ball and earn problem. If you think in terms of suits, that's like 42 balls split into 4 groups evenly of 13 balls with a certain color that we call a suit. Or we could split them into 13 different denominations, where each denomination is our different color. Again, something to just read in this last point. A lot of times problems you'll see, they'll emphasize that these objects are numbered so that you know that they're distinct objects, but you don't really need that. If you're told you have a set of objects and some of them are the same color, then 2 of the objects of the same color are distinct objects by definition. Again, if you're teaching like some kids how to kind of explore this, then yes, you would want to give them a bucket with balls, have numbers on them, and they could go through and actually count with their fingers one by one how many samples have a certain description. They could kind of write down all the different possibilities. But for us, it's not practical. We want to just get to the counting of these large numbers without having to do that. So first example, let's suppose a sample of 3 balls is selected from an urn that has 10 green, 2 red, and 4 yellow balls in it. So there's a total of 16 balls. So again, a sample of 3. So our sample space is the set of all possible samples of 3 balls. So out of 16, choosing 3, that counts how many different samples are possible. That's 560. So we want to know what's the probability of at least 2 green balls. Again, this can be done in many ways, and we'll see a couple different ways of doing this. Through partitioning, you break this into smaller categories. At least 2 green is the same as taking the case that there's exactly 2 green plus the case there's exactly 3 green. And we can split that even further if we want, but we don't have to, as we'll see in the next slide. The probability of 2 green can be broken up into a specific set, 2 green and 1 red, or 2 green and 1 yellow. Those 2 mutually exclusive pieces you can add. So by doing it that way, to count how many ways you can have at least 2 green, we consider those 3 cases. We can either have 2 green, 1 red, and 0 yellow, or 2 green, no red, and 1 yellow, or 3 green, no red, no yellow. That totals 390. So the probability is just 390 over the 560. Now again, keep in mind that n choose 0 is just saying how many ways can you choose no items out of a set of n items. That's always 1. So you don't have to include those, but up here it helps kind of see what you're doing. For each case, we're identifying how many of each type or each color we're choosing. So we could think, let's choose 2 green, and then once we choose that red, we're done with our sample, so we don't have to multiply it by 1. It's not going to change the number. So let's look at this example again. Instead of partitioning the sub-event exactly 2 green into specific cases, we can consider this as a single case with the multiplication principle. What we can do is a sample of 2 green balls means it has 2 green and 1 non-green. So we can relabel in our mind all the non-green colors as one single other color. And since there's 6 of those balls, we can just say, let's choose 2 green and then 1 non-green, or we choose 3 green. And then we divide that by 16, choose 3 to get the probability. And it's the same value. Let's look at another example. Same idea, same urn. Sample space is the same. What about the probability of there being at least 2 colors in the sample? Again, these are things you can do on the side. You don't have to necessarily show this, but just for organizational purposes. I want to split this up into mutually exclusive pieces that are each easy to count with the multiplication principle. I can break it down into 2 green and 1 red, 2 green and 1 yellow, 2 red and 1 yellow, 2 red and 1 green, 2 yellow, 1 red, 2 yellow, 1 green, and then 1 green, 1 red, and 1 yellow. And then we can treat each of those pieces as a multiplication principle problem and then add them all up. So again, 2 green and 1 red, or 2 green and 1 yellow, or 2 red, 1 yellow, 2 red, 1 green, 2 yellow, 1 red, 2 yellow, 1 green, or 1 of each of the 3 colors. And then just calculating what those numbers are, we add them up and get 436. So the probability of at least 2 colors is just 436 out of 560. Again, we can look at this one again from a different perspective. Probability of at least 2 colors is the same as the complement of that, I should say, is there being exactly 1 color. So the probability of at least 2 colors is 1, or 100%, minus the probability of having only 1 color in your sample. But in this context, how can you have 1 color? You can only have 3 green or 3... Oops, there's a typo here. Let me fix that. You can only have 3 green or 3 red. You can't have, or 3 yellow. You can't have 3 red. This 6 here should be a 4, and I have it correctly down below, but it needs to be fixed there. I'll fix that before I post these notes, but this should be a 4 choose 3, as it is here, so 1 minus this, and it's the same answer as we got before. So again, 1 color can only be done in 2 mutually exclusive ways. 3 green or 4 choose 3 was what should be here, choosing 3 red. So kind of in summary, I've gotten some of the things here. I'll just kind of show you quickly. You can read through these. Just kind of giving you a summary of some points to keep in mind when tackling counting problems. Again, the main thing to keep in mind is breaking your problem up into mutually exclusive pieces, each of which is easier to count by a direct application of the multiplication principle. What that means is, what you're really doing is, you're imagining this gigantic tree diagram, and you're breaking it up and organizing it in a way that you can easily count the number for each specific case or branch. And then once you've done that for all the cases, you add them all up. And I've also included in these slides are hints for the book problems. So I'll give you little hints about each of these, like what kind of problem is it, just so get you there, get you started if you have trouble getting started. And again, these problems vary from easy to a little bit more difficult, but you should be practicing all these. Keep going through them as you can, ask questions as you need. Ask questions in your journal as you're doing these. But I've given a little hints for all of these. The last few problems are a little more challenging, and I kind of go through an example there. Again, I'll let you kind of read through that, see if you can adapt it to doing those last couple problems. And again, ask questions if you need.